Thanks for the introduction, Alexei. Can everybody hear me? Okay, great. Hi, so I'm Samir, and this is joint work with Sebastian and Tim, who are over at London. Sorry for the change in the schedule. Maybe some of you are here expecting a different talk, but sorry about that, you're stuck. So quick introduction, I do research in machine learning and NLP in an intersection, and specifically I look at large collections of documents and try to see if we can extract some information out of it. That sounds kind of vague, but what we actually think about is putting that stuff into a database. And this is my research summarized in 3 clip arts. But what this means is that I have become both a user and a researcher of large-scale machine learning. And so during my PhD that Alexei briefly mentioned, I worked on Factory, which was a machine learning toolkit for a certain class of machine learning models. And it has a quite active user base, and they've been developing it since I left. But today, I'm going to be talking about this new toolkit that I'm working on called Wolfe. And the main goal here is to have a language that is universal in the sense that it can represent both current and future machine learning techniques. It's expressive in the sense that it's easy to write and modify models in the language. And it's modular, so you want to plug and play, you want to pick your favorite algorithm and be able to use it within Wolfe. And I'll also briefly talk about Moro, which is a software engineering side, on trying to create iPython-like notebooks in Scala. Okay, so I'm going to start with a brief application that many of you must be familiar with, just to sort of motivate Wolfe and the kind of stuff that we do. So here are 4 characters who like watching movies, and here are 5 movies. And what happens is, each of them goes and sees all these movies and gives a rating. Red is bad, green is good. And then the second one comes along and gives a separate set of ratings. The third one comes along, and the fourth one comes along, and you have a bunch of ratings for a bunch of movies. But you see that there are a bunch of missing holes there, and you want to finish this matrix. You want to figure out, what does the professor like? Does the professor like Monsters, Inc. or not? Does professor like Finding Nemo or not? And so, it should be pretty obvious from just this example is that the professor seems to be pretty close to Blossom there. And so he's likely to like the first movie and not like the second movie. And this intuition is kind of captured by matrix factorization, which takes this matrix, this sparsely observed matrix of ratings, and kind of approximates it with a low-ranked matrix. And so you get something like on the right here, where you have matrix U and V, which are much smaller than the original matrix, but they're much denser. And they kind of represent the similarities between users and movies. And so if we want to write it out mathematically, what machine learning in this scenario is actually solving is just a summation over all pairs that were observed, where xij is the observed rating. And you kind of want to see how close it is to your approximation. And if it is pretty far, you want to sort of change your approximation to make it as close to the truth as possible. Okay, so that's great. This is a very useful application. And you can also use existing toolkits to solve this. You can pick scikit-learn, and it has matrix factorization. But if you're here, you're probably not going to pick scikit-learn. You'll probably pick something in the JVM, maybe Weka or Mahout, or maybe Mallet, which used to be around. And if you're doing Scala, maybe you'll look at Spark, MLlib, or Factory, or there are a bunch of other toolkits, right? And that's great. They can solve this problem. They are pretty efficient at solving this problem. And they usually support a whole class of algorithms. So you don't just have to find one technique. You can sort of play around with a bunch of them. So this is great. You pick up one of these toolkits, and it solves the problem for you. But there is a problem. The problem is that machine learning doesn't really work until it does. And the point is that if anybody has dabbled in machine learning, you kind of have to repeatedly bang your head against it. And at some point, you don't know what exactly you did, but suddenly everything is working. and you want to get there as soon as possible. So the sort of things that you usually have to play around with, for example, are stuff like feature engineering. You have a bunch of features, you want to design your own features and mix and match. You have a choice of algorithm, and you want to run all of them and compare all of them, and they perform very differently from each other. But then also you read some paper or somebody tells you about this new method that you also want to try out, and there's just no code available for it. And then there are lots of other components inside each machine learning algorithm, like regularization, link function, loss functions, blah, 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 that you can all modify and sort of play around with, and some certain combination gets you great results, other combinations don't. And the problem is that it's not just 3 different categories, they are actually orthogonal to each other, so you have to try all combinations of all 3 things. And as a simple example of what you might want to do when you're doing machine learning is suppose you have an example like this, where you have ratings for the 3 Powerpuff Girls, but for Professor, you only have a single rating, which is that he doesn't like Incredibles. Now, that might make you think that he's kind of like Blossom, but 1 rating is kind of pretty noisy. But maybe you know that Professor is really good friends with Bubbles, and that they should basically have similar rating behavior. Sometimes they differ, like in this case, but otherwise they don't. Now, thinking about it mathematically, all you need to do is have a penalty to your objective function that says that don't make them very different. I think for whatever reason that they should be similar, just make them similar, right? Unfortunately, none of the existing tools that I outlined before can handle something even as simple as this. Now, this is not cutting-edge research. I just thought of it in a few minutes, but it's a pretty useful thing, and things like these keep propping up when you're doing machine learning. And so this is the problem when you're using existing tools. You might come up with a feature. It's possible that the tool doesn't support the existing feature. But even if it supports the existing feature, it doesn't support it with the certain other feature that you're interested in. And then for every toolkit that actually supports everything you want, you have to kind of learn the API. And there's a whole range of variants in there. You have to port all your data structures and your models into it. And then in the end, you're just still hoping it works. It could be all wasted effort. And in the end, a lot of times you just go like, I'm just going to implement it on our own. And that's often a bad idea. OK. So far, it's pretty clear, I hope, that machine learning, we can't use machine learning as a black box, right? You can't just throw some data at it and expect it to work. But we also know quite well that machine learning is quite complex to be a white box. They have decades of research going on, and people still don't understand what works, what doesn't, so you don't want to allow the user to tweak everything. And what we are looking at with this work is there something in between? Is there some power that we can give the user, but still kind of hide away some of the nasty details? In a sense, what we need is something that is universal and complete, by which it should be able to support existing techniques as much as possible. It should allow arbitrarily complex modifications to the code. But it should still be expressive in the sense that it should be easy for the user to set this up on their own task. And it should be minimal. They shouldn't have to do more than necessary. And also, because machine learning requires iterative development, the toolkit should support some kind of iterative development. So with this, I'm going to lay out a rough cartoon of what the rest of the talk is going to be like. Imagine that's the user. Initially, we're going to talk about language that the user uses to express his intention. Then an engine that takes that intention and tries to do something with it. And then finally, some sort of visualization feedback that lets the user know whether what he thought is actually taking place or not. So going a little bit deeper in the language, I mean the user is declaring the behavior that he expects from the machine learning algorithm. So like in the earlier case, we want the 2 bubbles in Professor to have similar behavior. That's the intention. And this kind of declarative definition can capture a bunch of whole models, as we'll see later. And then given this intention, the engine is there to basically perform those actions efficiently and scalably. And you might require a bunch of algorithms to be able to do that. And then finally, the user has to be able to make sense of what's coming out. And so you want to be able to debug the model somehow, which requires visualizing the output. So let's start with the first part, which is the Wolfe language. It's going to be a declarative and functional definition of what machine learning is doing. So let me have another cheesy quote on here. Machine learning is 20% inspiration and 80% optimization. And what we want to do is have the user focus only on the 20% and try to automate 80% as much as possible, right? So we named this Wolfe toolkit after this guy, Philip Wolfe, who's kind of the founder of mathematical programming and convex optimization and this whole slew of optimization research. And he has a bunch of algorithms that are used very widely in machine learning, but he himself is not a machine learning guy. So our Wolfe language, similar to the idea of mathematical programming, is very inspired by math, right? So what you're writing is essentially math. What makes it nice is math is universal. You can pretty much write everything. But what makes it tricky is you can easily write impossible and inefficient declarations as well. But the idea is that the user focuses on what they want the machine learning to do and leaves the how part of it to the Wolfe engine. But it's important to point out is that this is not a DSL. We like Scala so much that we feel Scala is pretty close to math already. We just had to add a few more operators. And the good thing is that since what the user is writing is Scala, it kind of integrates very well with existing code bases and pipelines and all those kind of things. And you can use compiler optimization, or in Scala's case, the lack thereof. OK, so let's talk a little bit in detail about the language. And I'm going to be focusing mostly on the language in this talk. So the first thing the user defines is the universe of things that you're performing machine learning over, right? And that's represented as a set of things. Then we have functions over those universes. So a common function that we use is something that takes an item of that universe and maps it to some double. And then we have these operators over these functions that take these functions and the universe of things and kind of do other things with them. And what I'm going to try and convince you is that all of machine learning algorithms can basically be composed of these things. Right? So let's kind of step through them one by one and see what they would look like. So first, let's look at what a universe of things is. Basically, the space of elements in the universe that you're performing machine learning over is a set of things. And so we have some default ones which would make sense, like Booleans and stuff are finite categories. So you have Booleans, set true or false. But we can also have infinite and uncountable sets, right? And this is where I'm going a little bit towards what the user wants to do and not so much about what the user, how we should actually do it. So we have sets that kind of represent the set of all integers, or even worse, doubles, which is the set of all real numbers. And then on top of it, you can have collections and you can have functions. So you have the first case is all possible sequences of Booleans, which can be infinite in length, and so obviously it's not finite. And then you have maps, which is all possible mapping from Booleans to infinite integers. So that the latter one is kind of like the family of functions. And then we have abstract data types as well. So in Scala's case, you can have tuples, and we can have all possible tuples. But case classes, since they're so useful, you can have a case class like person, name, and age. And then you can have all possible person objects with all possible strings as the name. Sorry about that. And all possible integers as the age. And so these are just, we're kind of defining what the set of things we want to do machine learning over are. And then we can also use the regular collection methods like filter on sets. But in this case, we kind of use it where because it's more mathematical. So we can say all persons where the name is Alexei, for example. Right? And so that's a smaller set. It's still infinite because the age can still be from an infinite range. But you're just kind of defining your space this way. Okay. The second thing you do is define functions over these universes. So most of them take off this form where they take an element of the universe and map it to a double, right? And so suppose you're talking about a Boolean domain, and you want to have a probability distribution over the Boolean domain. You can write something like this, which means you're just basically flipping a coin. But then in machine learning, you have loss functions and stuff like that. So in this case, it's taking a double as an input, and it's doing x squared. And that's your loss function for some case. And the idea is that you're composing these functions from the set of operators that Wolfe is defining. So we have a broad library of functions that you can use. You have the standard plus, minus, blah, 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 but also log and exponentiation, which kind of have special meanings in this case. These are different from the regular ones. But then you also have collections. So you can have apply and map on these collections, but you can also do sum over all these connections or product of all these things. And these are kind of similar to like fold left and fold right, but they have some special mathematical meaning in this case. And you also have vector operations because we do a lot of vector algebra. So you have cross product, which is the x. You have the dot product. You have the L1 norm, L2 norm, and concatenation of vectors and so on. Right. And so now given these functions, we have a way to do, we provide some operators to actually do something with these functions. So I'm going to kind of draw one of these examples where on the x-axis here, you have the universe of things. So the t is the label, but this is the set of t, and somehow you've projected it to one dimension. And on the y-axis here, you have the function that you're working with. So some function that takes each element of t and maps it to a double. So this is a pretty easy plot to understand. One of the major operators we have is the sample operator, which treats this function as a probability density and tries to sample from it. So in this case, maybe you call it 4 times, and this is the answer it will give. Right? So this is the kind of the semantics of that function. We also have an argmax, which in this case will go over the universe and find the maximum point. Right? And so you have an expectation, where you give another function, and it'll compute the expectation of that function according to this, to your function. And finally, there's this log z, which is basically the area underneath the function. Right? And so in this cartoon case, you can imagine it's pretty easy to compute it, but since I've been talking about infinite and uncountable sets, all these operators are not well defined all the time, which is fine. As long as what the user is trying to express can be solved, Wolfe will try to solve it. Okay. And so the idea is that the composition of these functions and operators can define machine learning algorithms, right? And so we'll go back to our recommendation systems example and see what it looks like in Wolfe. Right? So just to remind you, we have the universe here of movies and people. And then you have u and v, which are the parameters of your model. And those are, in some sense, part of your universe as well. And what you want to do is find the u and v that sort of solves this objective function, right? And usually when you look at the matrix factorization papers, there'll be a bunch of more terms, but you can imagine how that will fit in here as well. So the first thing to do is represent your original observation matrix just as a case class, right? So I'm just going to have case class x, which is one observation, which has I, which is the person index, and j, that is the movie index, and some score. Right. Then we have another case class representing the model parameters, which are both u and v. And so here we call it w for weights, which has u as a sequence of vectors and v as a sequence of vectors. And so the domain of both of these will be infinite and uncountable because they have doubles in there. So then what we do is we write our loss function, which goes over all your training data. And data here is just a sequence of x. And just a regular sequence. And what we're doing is we're summing over all of them. And for each of them, we are computing basically this score. We're doing the square of the rating of that observation minus the u of I, which is w.u of x.I, and then dot product with vj, which is w.v and u x.j. Right. And so you can see already that what you're writing here is exactly math, just kind of converted into Scala. And to some people, this might be even more readable than math. Right. Okay. All right. But then to get your actual W, you have to have this minimum thing also. Right now, I've only defined the sum part. And that's basically argmin over DOM of W loss. And the DOM of W here is, I haven't got it on the slide, but it kind of specifies all possible space of vectors, sequences of vectors, in fact. Right? And so now you can see how it basically looks very functional and very nice. And this would be a good way to look at machine learning. But now let's go back to our example of this case where the professor just had a single rating. And this is just the loss and the math from before. And what we were proposing of doing was having these two have similar behavior. And we were going to do that by adding this kind of penalty term to the objective. Now, in this case, we have our loss function, which is some function. And let's just add another function called preference, which doesn't depend on x anymore. There's only u. So you only have w as the parameter. And all it does is subtract the 2 and then does an L2 of it. This basically defines this operator. Now your new loss is sum of both of these. And so now instead of doing argmin over just the loss, you're doing argmin over the sum. And this way, you've just introduced a new feature that does not exist in the existing toolkits or even in literature. Right. Okay. And so now this was a simple example of how matrix factorization can be represented in this, but we've been looking at a whole family of models, and you can take label propagation, Bayesian networks, and I'm not going to read through all of these, but you can basically go through and imagine all of these models to be written in this certain way. Right? And what excites us a little bit with the recent advances is that this kind of stuff can also represent neural networks, right? Which is nice because, especially for Scala, there don't seem to be that many toolkits that can work with these kind of things. Okay. So this was the language, and so far it's all nice, and you can write all these models, but what actually can Wolfe do, right? And this is the part where we are regularly updating Wolfe and getting better and better every day and kind of covering more and more models. But I kind of want to talk to you about the ideology behind how we can support all these models. Okay. And so the engine here refers to the inference and learning algorithms that are efficient and scalable, that kind of take in these programs and do something with it. So the engine takes as input the declarative definition of the algorithm, right? And so the way to think about it is not that there's some function that has returned some value already, but that what you're looking at is the expression tree of what the user has written, right? So it'll be some expression tree of functions and operators that the user used to define what he wants to do. Now we can run these functions in many cases. If you're just summing over 10 numbers, it's still a valid operation. And basically we call it the brute force method, which works sometimes, but most of the time it's either impossible or completely intractable. Especially when you have doubles involved, it's not possible to do these things. And so what our idea is that we take this expression tree and apply transformations to it so that it becomes efficient. Right? And sometimes it means that you're being inexact. You're being approximate. You're introducing an approximation that didn't exist in the definition, but you're doing that so that it's actually tractable. And since it's machine learning, nobody really cares about correctness. They just want accuracy to go up. So that works for us. So I can't go through all the transformations that we have, but I'll give you a simple idea that sort of gives you a flavor of what we're doing, and maybe it'll be easy to sort of extrapolate that to the rest of it. So for example, let's take a simple Wolfe expression, where the domain here is the cross product of two integer ranges, right? So you have 0 to n, and you have 0 to m, and that cross is taking all possible pairs, right? And then what you want to do is you want to do an argmax over this domain, fa plus fb, right? gb. So what this means is you want the pair that gives you the highest fa plus gb, right? And it's obvious that if you just kind of go through this, since it's a finite domain, you can run through it, and it gives you O of n times m steps. And that's fine if n and m are small. But what you can easily do in this case, and it might be obvious to many, is you can kind of transform this expression by pushing the argmax in and kind of having two different argmaxes with a split domain, right? So this works because your domain was a cross product of things, but now you can have two different argmaxes, both of which are going over a much smaller domain, and so it kind of takes a linear time to solve this, right? And so this kind of gives you an idea of the kind of transformations we're looking at. We're looking at the expression tree, replacing some functions with approximate ones, but even doing some exact transformation that lead us to more tractable algorithms. And so if you're interested in more deeper machine learning stuff, this is an example of a CRF that we wrote. And then you have an argmax over all possible sequences when you're working with a CRF. And it's OK if you can't follow this. But the idea here is that we're looking at all possible sequences, which is in some sense a factored space. And we're looking at the definition of CRF, which also will look like a factored model in the same way as your domain. And this allows us to do belief propagation or message passing in this particular scenario, or junction tree, or a bunch of different algorithms. On the other hand, you can have another argmax expression, which looks fairly similar, except that the functions and the domains are very different. You have doubles here, but it's actually not that bad because it's a continuous space. And it turns out that what you have on the other side is also a smooth function over this domain. And that suggests that you can use gradient descent. And so what we do is we automatically differentiate this function and try to find the gradient and then follow the gradient to get the argmax. And if that function is non-convex, it will be approximate, and all these disclaimers exist. OK. So this is basically what the Wolfe engine does. I want to briefly talk about the scalability aspects. We are currently using efficient single core implementations because you need to get there before you start thinking distributed. And then we kind of are working towards supporting user-designed scalability. What this kind of means is that you specify Wolfe code and Wolfe operations inside Spark blocks so that it's easy to distribute. But then moving on, we are also looking at automatic scalability, where we detect independencies in the expression tree and figure out ways to split it up over multiple machines. And sometimes if there aren't any independencies, we kind of force them, which will make it more approximate, but still faster and still useful for what you want to do. One final thing that I do want to bring up is that in the engine, we don't, again, treat it like a black box. The user, if he doesn't want to care about optimization, he's free to just use it as it is. But you can also inject knowledge if you do have it. So for example, if you want to use max product BP for solving a specific argmax, you can easily add an argmax by and give it the parameters. You can also do, which actually makes it quite exciting, is have different models that do sample by using different algorithms, but then have a composition of those models that kind of uses each algorithm for its specific case. When possible. This is not always possible, but yeah. OK. So now I want to talk about the final part of my talk, which is going to be looking at the output of the engine. and try to see what the user can do with it. And specifically, I will be talking about Moro, which is the notebooks for Scala thing that we have. So part of our goal was to have an IDE that we can do machine learning in. Right? And it kind of means very different things from a regular IDE. But what we wanted to do in general when you're working with IDE is some interactive visual environment for debugging. Now, for machine learning, that means very separate things. There are actually 3 kinds of questions that come up when you're talking about debugging machine learning. The first one is you have to know what you're dealing with, what data input is it, what data output is it, and so you have to have a way to visualize input and output data, which is usually not just toString or something like that. The second question is, how is it happening? And even if something is working or not, like what is the declarative definition of how it is happening? And so for that, you need to surface to the user the details of the model. What they wrote actually reflects what their intuitions were, or is there some mismatch? And finally, even if they got the model right, things still go wrong all the time. And so then there's the question of why did this thing go wrong? And you kind of want to give the details of inference and sort of have a provenance to all your predictions when you're doing that. So in order to sort of get towards this kind of an IDD, we sort of started working on Moro, which is in some sense a browser-based Scala REPL, along with some notebook-like features. It's available as a separate toolkit from Wolfe, but kind of is part of the whole Wolfe toolkit. And you have to think about iPython notebook, but for Scala, and for people who are not familiar with it, it basically allows you to mix markdown, LaTeX images with code and execution. Right? But what actually excites me a lot was the visualization of Scala objects. So we just have a simple way to extend this where you provide an implicit converter that takes an object of your type and converts it to an HTML string. And as long as that is in the scope, the visualization just works. So since I have some time, I think I'm going to quickly walk through the demo that I have. I can't quite see the screen while I'm typing, so excuse that. Yeah. So this is what I'm doing is kind of writing out the matrix factorization code. And so in the top case, we just defined the case classes and for both the users and the weight vectors. And here we just defined an object of the case class, but when it renders it out, it kind of rends it out slightly in a more structured manner. We'll see a little bit more of that. Then I wanted to define some input to this whole thing, where here the inputs are the input ratings. So I have a bunch of numbers here that map pairs of integers to doubles, right? And we can try to toString them, and it basically looks like this, which is no more legible than what was in the code. We do convert them into case classes, and so it's possible to kind of run it and see the case classes, which is slightly better. By the way, this is all in Chrome, and everything is just running on my laptop. But this one looks slightly different, but it's basically mapping all of those input ratings into case classes. It's still not exactly what you want, right? And so all I do after that is kind of go through all possible pairs of integers and see what the rating is, and then just create this double-dimensional sequence. And if I run that, you see in a visualization, that's much more closer to what you would want. So you have 3 users here. Number of users was not easy to find, but you have 3 users here, 4 movies. The first one likes the first 2, doesn't like the second 2. The second one doesn't like the first 2, likes the second 2. The third one, we have a rating for the first movie. We just don't know the rest of it. Okay. And so if we continue, we can write our model here. This is the same thing that I had on my slides, where you just do the dot product. I kind of split it into more functions. There's some regularization here. But basically, the loss term is, again, the square of the difference between the rating and the dot product. And what we can do here, and it's not very legible, is just kind of look at what this score function is, which does a dot product. And in this case, all we're doing is calling the function, but it returns a Wolfe object that we can visualize as an expression tree. So you can't read this here, but there's a dot product, and then there's a sequence apply, which takes a specific vector. And then there are 4 vectors here corresponding to the 4 users, and 5 vectors here corresponding to 5 movies. 3 and 4. And then there are these constants, 1 and 2, that basically pick which vector we are kind of working with. Moving on, we can run training just by doing an argmax. And the output tensor just kind of looks nasty, so I'm just going to get rid of this toString and just do a regular case class visualization, which kind of lets us see all the user vectors right next to each other. And we can see, okay, the first and the last one look quite similar to each other. It's minus 0.8, both of them, 0.8 and minus 0.4, 0.5. And the second one looks kind of nasty. Then suppose we want to go and predict something. We have a prediction function that basically calls the score function. And we can call it with individual numbers. So we can do 2, 2. We can do 2, 1. But all of this, again, it's not really clear how to visualize this. So then we go back to our matrix visualization, which goes over all pairs of numbers and calls predict on it. And here we can get a prediction. So now, earlier on, we had these 3 things which we didn't know what they were. And now those are filled in. And this is just a simple notebook that kind of shows the whole pipeline. The rest of the demo here basically adds this additional preference factor that I talked about, and a new loss that is sum of the old loss and preference. And then when you look at the weight vectors, now it's trying to make 1 and 2 similar. So now you can see that 1 and 2 are kind of similar. They're not exactly the same because the observations are different, but you get a similar weight vector. And then when you actually visualize the predictions, these 2 are more similar than they were before. Like earlier, they were completely different. Now you can see some light shades here and dark shades here, and they're kind of getting closer towards each other's behavior. Okay. And so this was just a simple demo, but we have visualization for factor graphs and all other kinds of graphs, and NLP-specific tagging stuff, plots, regular social network kind of graphs, and images, and all kinds of things. Okay. So in conclusion, I hope I've convinced you that machine learning is inherently iterative. You need to try many algorithms, many variations, many techniques, and it's kind of unreasonable to expect that a single toolkit will actually solve all of them efficiently, but we still kind of want to move towards it. And particularly, we are interested about using this language as an interface that allows other people to maybe plug in their inference algorithms into the same framework. So towards that, we introduced Wolfe, this math-like language to express whatever you want. And the Wolfe will try to solve it for you automatically. Sometimes it will succeed, sometimes it will fail. And then we also talked briefly about Morrow, the notebook for Scala that kind of is designed for this iterative programming paradigm. So there are a couple of future things that we want to look at. We obviously want to continue supporting more models and inference algorithms. And we are still researchers. We are still reading papers and implementing them in our free time. We definitely want to move towards distributed computing backend, probably using Spark or something similar. And any ideas towards this actually would be quite helpful. We want to clearly document what is supported and what is not. And this is one of the tricky things with a language like this is user wants to write something that obviously we haven't imagined yet. But then we also want to guarantee to them that it'll work. And so there's some work to be done there. And we want to continue expanding the visualization support that exists in Morrow. So if you have any questions or any comments, please reach out to me and get in touch. Thank you. If there are any questions, please.
So the user will write some equations, and there will be any way for the user to help the system use the actual algorithm in case that it turns out to be impossible or too difficult, or the algorithm isn't good enough.
Okay, so the question is, it's a pretty good question. The question is whether once the user writes a model, is there a way for user to guide Wolfe into a better algorithm if the first one seems to be really bad? And that is definitely our goal. That's what we want to do, which is why we are kind of supporting this visualization of the model independent of the inference as one layer of visualization. But then once the inference algorithm comes in, how is belief propagation happening? How well is it doing? At what point does it seem to be plateauing? We want to kind of surface all these details to the user, and that way the user can get an idea of which part of the model seems to be working, which part is not working, and if he just gets rid of one part, will everything just be really fast? And so, yeah, that is definitely the eventual goal. We're there partway. Yeah.
So we have Jupyter Notebook, we have Spark Notebook, we have Zeppelin, and we have Mora.
Right.
Beautiful.
Right.
How do we, as a community, converge, if possible, to converge in a single notebook for Scala,
Right.
so that we can basically give it to the world as Scala's recipe for the design? So out there, we carry obstacles to kind of do this, and we need to have Centerpoint.
All right. That's a good question. The question is, there are a bunch of existing toolkits that look a lot like Moro and IPython, like Jupyter and Spark. People have their own, and a bunch of others that I'm not familiar with. But yeah. So when we started Moro, it was about maybe 2 years ago, where none of these things were at least not public. And Moro for me is becoming a lot more of a pedagogical tool. So I'm using it more for courses and classes and for sort of documenting my own stuff. And it's not clear how much, how much more it will be useful to compared to something from Spark, where they have a team of engineers working on it. What I like about Moro is it's a little bit more focused towards machine learning and NLP and stuff like that. And that I haven't seen so much. Unless you're using MLlib, the other one wouldn't be that useful. Moro can be used without any of the existing stuff as well. And it's easier to extend and things like that. But it would be good as a community to sort of start focusing our efforts towards maybe one or two, but yeah, something. Yeah, good question. Right, so the question is, Wolfe is still fairly, I'm going to be paraphrasing a bit of it, but Wolfe is still in its fairly early stages where not everybody will find it useful. And so the question is, what is the development plan, and when do you anticipate people to start using it more regularly or more reliably? So that's a good question, and that's something we struggle with. A lot of the questions that we are trying to address are open questions in the research community. It's not clear how you go from this expression tree and always have something that's efficient, even if mathematically there is a reduction there. But what we do, so what we've tried to do is use Wolfe for our own research. And so already we have a group of researchers doing research in machine learning and NLP, trying to use Wolfe and trying to support a broader range of models. And I think it depends on the kind of user you are. If you're looking for something that you have a specific model in mind, you don't want to read up a little bit more about the math or anything like that, then Wolfe right now may not be perfect for you. But if you are using tools and you're hitting a block that you have some ideas about how to address, then Wolfe becomes a pretty useful tool, even right now. And yeah. So the question is how much our expression tree transformations has in common with compiler optimizations and the stuff that Spark people are doing. I'm not too familiar with what the Spark people have been doing in terms of optimization, but as far as compiler stuff goes, we kind of think of it as orthogonal solutions. We still want to use all the compiler optimization, so everything we do ends up being Scala code that goes to the compiler, so those still exist. But what we are doing is a lot more optimization at the level of mathematical approximation and optimization, which is like mathematical optimization, not compiler optimization, which ends up being very different in flavor. There are definitely interesting theoretical or formal definitions of the semantics of transformations that we would like to use in Wolfe that comes from the compiler community. And there are some interesting approximate programming work that could be part of what we are trying to do. And there are definitely connections. We haven't been looking a lot into it. Yeah. Any other questions? Okay, thanks.